you know. So I should have told all the jokes that I don't want recorded before that, right? So if you had warned me, I would have. In any case, anyway, so let me begin with this talk. So I haven't given a Zoom talk in a while, so hopefully, it'll be a sort of a refresher in how that technology works. So I want to talk about the cohomology of the mapping class group or the moduli space of curves. So let me begin by introducing my notation and the sort of basic definitions. So oops, that's the eraser, not the pen. So I'm going to denote in this talk, so sigma G, that right there is going to be a closed genus. And the G is always going to be at least 2 surface. And so mod sub G, that right there is the mapping class group. And by definition, what is that? We take the group of orientation preserving diffeomorphisms of our surface, and we mod out by isotopy. Or we take pi naught of that topological group. So this is what I want to talk about today, and I guess the main topic is the cohomology of mod G and its subgroups, which I can't spell today. As I said, I haven't. So I'm during the height of the pandemic, I could write on my iPad faster than I could write with chalk, and I'm losing that power. So it might even slow me down. And it's sub. Okay. So now, what do I mean by the cohomology of a group? So definition. What this means. So for a group G, just to have all of our stuff here. I know this is a topology seminar, and it's and you all are not just topologists, but you're even more of an algebraic topology department than we are. So maybe I don't need to tell you this, but just in case, when I talk about the homology or cohomology of G, that is by definition the homology or cohomology of a K G1. So that means a space whose fundamental group is G and whose universal cover is contractible. Okay, and so the reason, why do you care about the cohomology of groups? There's sort of algebraic and there's geometric reasons to care about it. The algebraic ones are the sort of more obvious thing. These provide obstructions to various sorts of group theoretic things like extensions and things like that. But the topological reason to care about things like group cohomology is that KG1s, well, it turns out that a lot of the most beautiful spaces in mathematics are KG1s. And so the theory of group cohomology gives you a sort of entry point to studying the cohomology of spaces that you might care about for a totally unrelated reason. So it gives you a point of view, it gives you a source of spaces that turn out to be quite beautiful. And so I'm going to begin by telling you the most important model for the cohomology for the KG1. So this is the model for a K mapping class group 1. Okay, so it starts off with the following amazing coincidence. So amazing. You're only allowed to say the word amazing if it's not your theorem. Coincidence. Say CI. And thankfully, this is a theorem of people that no one's going to complain about. I think Gauss is one of the people I need to put on this. So the following structures on sigma G are the same. Following structures on surface sigma G are the same. I'm going to give you several of them. The first one would be a conformal structure. So that's just the data you need to measure angles between tangent vectors. Maybe you don't know the lengths of tangent vectors, but you can measure angles between them. Another structure you might put on there would be a hyperbolic metric. So a metric of constant curvature -1. It turns out that inside every conformal class, there's a unique hyperbolic metric that realizes that conformal class. Okay, so that's so metrics of constant curvature -1. Another structure would be the structure of a Riemann surface. So a complex manifold of dimension 1. So if you endowed the surface with that, it turns out that's the same as a hyperbolic structure and the same as a conformal structure. And the final one would be the structure of a smooth smooth complex variety. So the vanishing locus of a collection of polynomials in projective space. So these are all very different parts of mathematics, right? And so you should never, when you see this coincidence, when you first learn about it, you should think that these are different worlds, and you should be surprised. I mean, in fact, you still should be surprised, even if you've seen the proofs and you've gotten used to it to the point where this is part of your working mental landscape of the world. So every equivalence here is a non-trivial theorem. So as an example, let's say that I wanted to get from a let's say that I wanted to get from a hyperbolic metric to a Riemann surface structure. What I would do is I have my hyperbolic metric, and what I would do is so in fact, if I have any metric whatsoever, I can find what are called isothermal coordinates. So I can find coordinate charts which identify the conformal structure given by the metric with the conformal structure of an open subset of the complex plane, just the usual conformal structure. And the transition maps are conformal maps, so that gives you a conformal structure, and conformal maps between biconformal maps between open subsets of the complex plane are also called holomorphic functions, or biholomorphic functions. So that gives you a Riemann surface structure. So all these and also all these different equivalents, all these different ways of going between these different structures, they're all highly transcendental. They're all they sort of they're none of that. So they give you a whole bunch of different tools for thinking about these things. Okay, so now once you have all these structures, one feature of them is that you can deform them, right? So if you have a hyperbolic metric, well, you can deform a metric, right? Metric is just you have an inner product on every tangent space. You can start varying that, and you can vary it through hyperbolic metrics. You can deform Riemann surface structures. You can deform the structure of a variety very easily. If it's the vanishing locus of a bunch of polynomials, you can vary the coefficients of the polynomials. So all these structures vary, and so definition, so Mg is equal to the space whose points are isomorphism classes of such structures on the surface sigma g. Okay, now anyone that's a real expert is going to say that's not real. There's not really a space of such things, and that's this is really instead of the word space, I should have written the word stack. But we're just going to pretend that that's not an issue here. So this is a space. So as you move around the space, it's every point of the space represents, say, a different Riemann surface structure you might put in your surface. And as you move around the space, you're varying that Riemann surface structure. So it's sort of like the way the Grassmannian parameterizes different, say, three-dimensional subspaces of C to the 7. And as you move around the Grassmannian, you're varying the three-dimensional subspace. Well, this is the same sort of thing. It's like the Grassmannian of Riemann surface structures or hyperbolic metrics on your given surface. Okay, so now what does this have to do with the mapping class group? So here is a theorem which is due to Fricke and Klein. They wouldn't have stated it like this, but it says that Mg is a K mapping class group, comma 1. So this is saying two things about it. It's saying that its fundamental group is the mapping class group, and it's also saying that its universal cover is contractible. Its universal cover is often called Teichmuller space. So this is how Fricke and Klein thought about it. So now I'm not going to be able to prove that to you. I don't really want to talk about Teichmuller space, but I do want to make it not totally crazy. So there's a question here, is how to see that the fundamental group pi 1 of Mg is equal to the mapping class group. So there should be some sort of map between these two things. I'm going to copy this so I can move it to the next screen. Copy. Because unfortunately, this is actually one, I can't advance my slide so that the right side stays visible and just moves to the left. That's not how the way my iPad works. So I want to explain how this works, because this will also move us into one of the next things I want to talk about. So I'm going to move to my next slide, and I will put this question. If I can paste it, I can move it to the very top right there. Okay, so how can we see that the fundamental group of Mg, of this space that parameterizes Riemann surface structures or hyperbolic metrics on my surface sigma g, what does that have to do with the mapping class group, with diffeomorphisms modulo isotopy? So we have a the answer for this is that we have what's called a universal curve. So, which is usually rated as mg1 mapping to mg. So first mg1 is pairs. So you have S comma P with S a point in mg, so a Riemann surface structure, and on sigma g, and P is a point inside S. Okay, so you're parameterizing not just a Riemann surface, but also a point on that Riemann surface. So with that, so this, the map from mg1 to mg forgets the point P. Okay, you just delete that point P. So we have this map right there. So we're putting above every point inside mg, we're putting a copy of that Riemann surface. Okay, and so then this actually forms a fiber bundle. So this is a fiber bundle. So we have the fibers are all copies of sigma g, right? They have a Riemann surface structure, but just as topological spaces, there's sigma g. And we have a map to mg1, and we have that projects down to mg. So, and again, people that know about the technicalities of the subject know that I'm working in the category of stacks. This is the world of stacks is set up so that this is a literally true statement. But you just have to reinterpret what a space is. In any case, though, we have this fiber bundle right here, and what this means is that whenever we have a fiber bundle, we have above every point is a copy of the surface, and as we go around loops in mg, and you look up at the surface above you, well, the surface twists up, right? Like it gets just deformed, and it comes back to itself in a twisted way. So above loops in mg, so the fiber sigma g, twists and turns. And when you come back to where you started, you have some diffeomorphism of the surface. So this gives you, so thus, the return map, when you get back to where you started, we get some, map, we get some map, from the surface, the original fiber, we get some twisting to sigma g. And so, which is well defined up to homotopy. And so what this gives you is what's called the monodromy representation, which goes from pi1 of mg to, well, it's going to give you a diffeomorphism orientation preserving as you go around a loop. But then there's a lot of choices I have to make, and including the loop is only well defined to homotopy, and so up to isotopy. And so that right there is equal to the mapping class group. And it turns out that this right here is the isomorphism. So this is why the fundamental group of mg is the mapping class group. For above every loop inside mg, you look at the corresponding fibers in mg1, you go around a loop, you get an element of the mapping class group, and you prove that that's actually an isomorphism. So and that reflects the fact that that mg1, this universal curve, has a universal property. It's the sort of universal it's the universal fiber bundle whose fiber is sigma g. Okay, so that's what this has to. That's what the that's the topological model that you should have in mind when you're thinking about the cohomology of the mapping class group. The cohomology of the mapping class group, so, is the same thing as the cohomology of mg. Well, as a stack, if you don't really want to talk about stacks, it's true. This is true rationally, just literally as spaces. And so everything I say in this talk will be about rational cohomology anyway. So there's no way that you could possibly be confused about this. Okay, so that is, I have to get my thing so I know exactly what time it is. That is the sort of geometric space to think about. I want to talk about the cohomology of of MG. So I should give you some cohomology classes, so so you can sort of see how these things work. And this universal curve, this fiber bundle, is going to play an important role inside. Let me copy that when I want to construct cohomology classes. So what I want to do is the next goal is I want to talk about what are called the kappa classes. Oops, that's the wrong thing. So it's the So these are classes kappa n. It's going to lie inside the 2nth cohomology of the mapping class group, or of MG, let's just say with rational coefficients to play it safe. Okay, so I want to construct a class that lives in degree 2n. So how can I do that? Let's start with the universal fiber bundle, the universal curve. So, which I was going to paste, but there's no reason I could just write this again. And so what can I do with this thing? What I can do is, I can construct what you might think of as the vertical tangent bundle. What this is, so I'm going to let V sub V, this right here is equal to the vertical tangent bundle. And so what this is it's, if you call this map right here, say pi, what this is actually, I shouldn't call that. Yeah, I'll call that pi. I'm going to have I'll have several pi's floating around. So it's the kernel of the map T pi going from the tangent space of MG1 to the tangent space of MG. So this is just a two-dimensional vector bundle. They're exactly the tangent vectors that lie tangent to the fibers. Okay, that's why it's called the vertical tangent bundle. So this is a this is a vector bundle, let's see. So I have to. Sorry, my brain shuts off if I'm not careful there. So this right here is a vector, it's a sub bundle, the tangent bundle over MG1, right? So this is a sub bundle of the tangent bundle to MG1. So it is, we have R2, that's the typical fiber, goes to the vertical tangent bundle, and that goes to MG1. And so once I have I have a two-dimensional vector bundle, and so it has an Euler class. So we get an Euler class. So E of V, and that lies inside, H upper 2, the second cohomology of MG1, right? Again, I want to use rational coefficients here. And so I could take powers of this Euler class, and those will give me even dimensional cohomology classes, but in the wrong space, right? These are even degree cohomology classes over in MG1, and I really want cohomology classes on MG. That's my real goal. And so remember, I have this map right here. So we also have a wrong way map, which we'll call pi upper exclamation point. That goes from H K of MG1, again, with Q coefficients to H. Well, it drops cohomology by 2, drops degrees by 2s to MG with Q coefficients. There's lots of ways to construct this. The sort of simplest to tell you just in words is represent cohomology classes using de Rham cohomology. If you do that, these are differential forms, and you have a fiber bundle. You can integrate a differential form along the fibers. And what that does is it drops the degree of your differential form by 2. You've used up 2 of the dimensions, and so it takes a form of degree k to a form of degree k minus 2, and that gives you exactly that gives you a map on cohomology like this. It's not a ring homomorphism. It's just a map. Okay, I mean I guess it's a homomorphism of abelian groups, but it's not a homomorphism of rings. It doesn't respect the cut product structure. And so then we define, and we'll call this thing kappa n, what that is going to be, oops, why is that not equal to, we take powers of the Euler class and we raise that to, well, we'll raise that to the n plus first power. And you see that lies in degree 2n plus 2, and then I want to make that, and we drop the degree by 2, so that does lie in degree 2n of mg with, say, rational coefficients. Okay, so these are the basic classes. They were constructed independently by Morita, by Miller, and by Mumford. And so we get a, so these classes assemble, each of them lies in different rings, so we get a ring map. Goes from the polynomial ring and the kappa classes, kappa 1, kappa 2, and so on. That goes to the cohomology ring of mg with q coefficients. And so there's a deep theorem of Madsen and Weiss. This was a conjecture of Mumford that says that this map, which I'll call maybe call it phi. So phi is an isomorphism. So in degrees that are small compared to the genus. So in degrees that are, much less than the genus. Okay, so if you fix a degree, like you're looking at degrees, degree 5 cohomology, well, eventually it becomes the degree 5, as the genus gets bigger, eventually it becomes the degree 5 power of that polynomial ring, which is of course 0, right? Because I chose 5 to be an odd number and all these classes have even degrees. Okay, so this is, so these are basically the only cohomology classes that we really understand for MG. So it turns out that it's known that there's other cohomology classes. We even now have explicit constructions of some of them, but these are the only ones that we really have any sort of geometric control over. Okay, and the theme of the talk will be other sort of stable phenomenon. So I don't need to actually talk too much about the unstable cohomology. Okay, so are there any questions? It feels weird, like I can barely see people's facial expressions, so it's hard to read the room, but I'll pause. Are there any questions? Okay, good. I see some thumbs up. That makes me happy. Anyway, so what was that? Oh.
Sorry, real quick. Is there a more precise statement on this last theorem, or is it just complicated to spell out, or is there an actual?
It's on the order of 2/3 G, like maybe 2/3 G minus 1. I always forget the exact additive. It might, but it's something along those lines.
Okay.
So anyway, let's move on. So there's one sort of phenomenon here. So that one consequence, which I don't want to spell out, is that these what this means, but this is going to come back later. One consequence is that I just have this right here, is that the cohomology is independent of G once G is large. So this implies that H, K of mod G is independent of G for G large relative to K. This is a theorem of Hare, actually. This is what's called homological stability. And in fact, it's one of the ingredients that goes into the Madsen-Weiss theorem. You need Hare stability to prove this theorem. So the first step, the first thing which was proved in the 80s that this is actually independent of G once G is large. Okay, we'll come back to that a little bit later in the talk. Okay, so now I want to talk about a related phenomenon. So there's an analogy between, on the one side, the mapping class group, or MG, and on the other side, arithmetic groups, like SL and Z. And it turns out that a lot of these phenomena also hold for arithmetic groups. So Borel, long before Madsen and Weiss. So Madsen and Weiss was like 2003 or something, and Borel, I think it's 73, but I'm not. It could be 76. I forgot to put that in my notes, so I don't remember. What he did was he calculated. So the stable cohomology of SL in Z, and in fact, many other groups as well, at least rationally. So we still don't know the stable cohomology integrally of these groups. That's related to the fact we don't actually know the algebraic K-theory of Z completely, even though we know most of it at this point. So this was a, so I think of this as like the Madsen-Weiss theorem, but for the group SL and Z instead of the mapping class group. And all the other sorts of things. So like the independence of the cohomology of the degree once the degree is large. So that's homological stability. That was also proven for these things. In that case, that was proven integrally by Charney and Mazin in their independent PhD. They both wrote PhD theses proving this at the end of the 70s. But I want to make an observation about this, about Borel's proof. So Borel's proof was very soft. So it did not use the fact that we were working with SL and Z very much. It only used the fact that SL and Z is a lattice in SL and R. Well, you might think, okay, that's fine. So you can compute the cohomology of any lattice. But the important thing is that the answer you get doesn't depend upon the lattice. So Borel gave a very simple, it's also a polynomial ring, just in slightly different classes and somewhat different degrees. But the answer you get the same answer no matter what lattice in SL and R you need. So so this is an amazing fact. So the answer is that the cohomology of gamma with Q coefficients of a lattice gamma in SL in R, so is independent of gamma in a stable range. And there are many lattices inside the Lie group SL and R. SL and Z is the easiest one to write down, but there's many of them. There's some that are co-compact. There's all sorts of different things. They all come. It turns out that in at least 3, they all come from arithmetic constructions. That's what Margulis won the Fields Medal for. But there's lots of them, and there's no simple way to relate them. So it's sort of a crazy fact that their cohomology, at least in a stable range, doesn't depend upon the lattice. And so let me, so I don't want to write down an arbitrary lattice that would require, you can parameterize them, but with fairly complicated arithmetic data. But there's one lattice that's easy to write down that's not SL and Z. So let's let gamma n of L. This is what's called the level L congruent subgroup. This is the kernel of the map from SL in Z to SL in Z mod L. So L is an integer, at least 2. Right. So this right here is a find index subgroup of SL and Z, hence a lattice. And what the above implies is that in a stable range, so the cohomology HK of gamma n of L with Q coefficients is isomorphic to the actually I'm going to switch to homology here. It doesn't, that makes the map go the right direction. That's sort of more appropriate for what I'm doing right now. You look at the kth homology of SLN Z with Q coefficients. Okay, so passing to this find index subgroup does not change the rational homology, and at least in a stable range. Okay, and so this is to my mind, a fairly surprising fact. So this is sometimes called the Borel stability theorem. And so it's a different kind of stability than the sort of ordinary homological stability that I alluded to previously. So the ordinary homological stability, you're increasing a parameter. You're going from, say, SLN to SLN plus 1 to SLN plus 2 and so on. Here, we're taking SLN, but we're making it smaller by passing to a congruent subgroup. Okay, but neither one changes the cohomology. So remark is that this is only true. This is false with Z coefficients. So this is very much a rational phenomenon. It's also false outside the stable range. And it's false with Z coefficients. Also, it's false outside the stable range. There's, in fact, there's, they turns out that the rational homology of SL and Z and gamma n of L, these are quite different once you get outside the stable range. It's not, the difference is not completely well understood. Anyway, so the what I want to talk about now is let me check. Yep, I'm exactly where I have to check my watch. Sorry. So usually I can see the clock in the room, but I can't see where the hands are. So I have to actually look at my watch, to tell you. I can't pretend to not be noticing the passage of time. So what's the goal? The goal theorem is an analog of this for the mapping class group. Okay, so what happens to the mapping class group when we pass to a finite index subgroup? What happens to its cohomology? Or equivalently, you look at the moduli space of curves, of Riemann surfaces, you pass to a finite cover. What happens to its rational cohomology, at least in a stable range? Okay, and that's what the main theorem I want to talk about is about. And so let me state it. So I said, it's the subgroups of SL and Z that are easiest to write down, the finite index subgroups, are these ones right here. It turns out that these actually are, at least once n is at least 3, these are cofinal in the finite index subgroups. That's a theorem of Bast-Milner Serre called the congruent subgroup property. Actually, I guess that's Minicki and Serre. So this Bast-Milner Serre proves something more general. But so I want to talk about the subgroups of the mapping class group that are closest to those. And so those are what the linear congruent subgroups. And so how do I define those? So define, so well, so I want to notice I guess I'll say it right here before I state the define. So the mapping class group, remember, these are diffeomorphisms up to isotopy. Well, of course, that acts on, say, H1 of the surface, with whatever coefficients I want to put there. Let's put Z mod L coefficients, okay? So we have an action of the mapping class group on the first homology group of the surface, because, and so definition, so mod G of L is equal to the kernel of this action. Okay, so it's the subgroup of mapping classes that act trivially at homology mod L. And so now this action, this preserves the algebraic intersection form. And so we have a map from the mapping class group. So it's to the automorphisms of first homology. And so, as I said, since that preserves the algebraic intersection pairing, which is a symplectic form, that's SP2G Z mod L. So I hope that's readable. And it turns out that's surjective, and the kernel is mod G of L. So that's the group right there. You can see that's sort of similar to the kernel of the map from SL and Z to SL and Z mod L, the sort of mod L reduction map. It's somehow, so these are the ones that look the closest to that. And my theorem, like, literally is the same thing that Borel proved. So it's the following. So P, which says the following. So let's fix. Let's see. So it's I'll just state it like this. So it says that HK of mod GL with rational coefficients is isomorphic to HK of mod G with rational coefficients in a stable range. So G is greater than or equal to, and I actually wrote the formula here because, since that's, it's 2K squared plus 7K. Why is my pen not working? 7K plus 2. Just the formula you expect, right? I don't know. That's clearly not sharp. It's just, so I should say, by the way, so ordinary homological stability and Borel's theorem, they both have a linear range, and this is quadratic. So I don't, I think that it would require a new idea to improve that quadratic range to a linear range. But probably the coefficients, like the 2 is probably hard to improve. The 7 and the 2 are probably very improvable by with a little bit more work. Okay, and I should again remark that the same caveats that I said for Borel's theorem are also true here. This is really false over Z. Even for H1, this is not true over Z. And it's also very false outside of the stable range. So there's calculations of, I guess, myself and Tom Church and Benson Farb, and also myself and Neil Fullerton, that sort of show what happens near the cohomological dimension. And these things are quite different in those degrees. Anyway, so this is the theorem. So I guess, what I want to spend the remaining time of my talk doing is saying a little bit about what kinds of things might go into the proof of this. Okay, but before I do that, are there any questions? So again, it's awkward, like I feel I can't see this. I can't see people's faces very well. So I'm doing and so I'm doing that very mathematician thing where I'm telegraphing my awkwardness by talking about it. So, anyway, so let's see here. So I think what I will do is I said, I'm going to go. So are you talking, Sasha? So
it was me talking. So is there any chance that this is still true for like all of the finite index subgroups, or is it specifically something for the symplectic group?
So yeah, that's a good question. So this is an open. So this is a conjecture I'll make. This is true for all finite index subgroups, but this is open even for H1. So even for H1, so this is actually a famous conjecture of Ivanov, which would say, well, the first Betty number of the mapping class group is 0. So the abunization of the mapping class group is trivial once G is at least 3. And so this would say that the first Betty number of any finite index subgroup of the mapping class group was 0 once G is sufficiently large. That's a fairly famous question. There's been a lot of work on it recently. It's known in many examples, but we're nowhere close to even knowing that. So I think that this theorem is the only thing that's known about higher homology groups. So are there any other questions?
Would that follow from the congruence subgroup property for the mapping class group?
No, it would. So the congruent subgroup property is not known to imply that. So I guess one thing that I guess one thing that's known. So there's a theorem of myself and Ben Wieland that says that you don't even need the congruent subgroup property. So independent of the congruent subgroup property, if you can verify the statement for H1 for all congruent subgroups, then you would know it in general. So strangely enough, so that's the proof of that's pretty. So okay. So now I'm talking to like the one or two people that know the word congruent subgroup property of the mapping class group. So there's a very famous false proof of that by Marco Boggi. It appeared in like Mathematische Nachschriften at some point. And so the proof that Ben and I have about the first Betty number of finite index subgroups, if they're ever non-zero, they're non-zero for some congruent subgroup. That actually uses some of the ideas from Boggi's false proof of the congruent subgroup property. There's some Hodge theoretic results inside there that we use, and so it's not unconnected. So like I am using something about the congruent subgroup property there, but that's definitely wide open. So anyway, so if there are no other questions,
can I interrupt?
I have a question.
Okay.
Maybe I can hear me better.
Okay. What kind of consequence does it give for the cohomology or homology of the Torelli group?
So that's a good question. So I think the consequences would go the other direction. So the Torelli group. So it turns out that if I knew the most optimistic possible thing about the cohomology of the Torelli group, then it would imply this theorem. So if you knew that in a stable range, the homology of the Torelli group was finite dimensional, and not just finite dimensional, but also a rational representation of the algebraic group sp2g, then that would imply my theorem. So, which of course those are, maybe they're true, maybe they're false, I don't know, but we only know that for H1. So, and in fact, you can prove the theorem for H1 using those statements. That was actually done by Dick Hayne many years ago. I should have said that. So the theorem was earlier by Hayne, little one, and me about a decade ago for K is equal to 2. Okay, so anyway, so yeah, so yeah, and so Hayne did that using the homology of the Torelli group, but this somehow the progress in the homology of the Torelli group, there hasn't been that much progress in the last 10 years or so, and it's definitely not enough to prove this theorem. So okay, so let me give just a few basic ideas about the proof of this right here. Just looking at my watch. So your first idea is, well, I told you that the way Borel's proof worked was that he did a calculation of the homology of a lattice in SLN-R, and he got an answer that didn't depend upon the lattice, right? So your first thought was, oh, well, Madsen-Weiss calculated the homology of the mapping class group. Why don't I just imitate Madsen-Weiss's proof, right? But just try to, just in this for these more general groups, and that's just not going to work. I think the main issue for that would be that, so the starting point of what Madsen-Weiss did is they identified the homology of the mapping class group with the homology of some kind of infinite loop space, and it's not clear that the infinite loop space multiplication structure is no longer commutative. Like the corresponding multiplicative structure you get on the homology of these congruent subgroups is no longer commutative. So therefore, like any sort of infinite loop space techniques aren't going to work. It's not even clear that it's the homology of an infinite loop space. So you have to do something different. And so what I'm going to do, I want to tell you first a sort of basic fact about covers. So here is a little basic fact. I can't spell today. Fact about covers. This is something that you could easily teach in like an undergraduate course in algebraic topology. Like if you told people about H1, you could prove the version of this for H1. So what does it say? It says that let f from x tilde to x be a regular cover with deck group G. So, and here I'm assuming that G is a finite group. So you have a finite regular cover just of reasonable topological spaces, say CW complexes. And I think actually you can do it with I don't think you need any assumptions in the space. And what it says, it relates the homology of X and the homology of X tilde, at least rationally. So what it says then, I'm going to state this for cohomology. So if you take the kth cohomology of X with rational coefficients, that's the same. Well, let's take the kth cohomology of the cover with rational coefficients, and let's take the G invariance. Okay, so that's what that superscript means. That's just G invariance. Okay, so this is just a basic fact about the cohomology of the rational cohomology of covers, is that you can, and so as I said, it's pretty, and it's elementary. Like it really just comes from thinking about how the group G acts on the chain complexes, computing these things. So, okay, so what do we have? What consequence does this have? What this implies, so, is that to prove that to prove that, I guess I'll move to prove that that isomorphism holds right there, the one that we're trying to talk about. What do you have to prove? It is enough to prove that, so this corresponds to like a finite cover of a KG1 for the mapping class group, right? The deck group is going to be the quotient, so it's enough to prove that mod G modulo mod I guess GL acts trivially on, say, the cohomology of mod G of L with Q coefficients, right? That's, if you could show that that action was trivial, then when you pass to invariance, you don't actually do anything, right? It just everything is invariant. And in fact, it's not just enough to prove that, like these two statements are literally the same statement. Okay. And so that's what we have to show. And so, so the action, of course, this action comes from the conjugation action of the mapping class group mod G on its normal subgroup mod G of L. Okay, so we want to show that conjugation action induces the trivial action on rational cohomology or homology. Okay, and so how can we do that? Well, we're going to check this on generators. So I'll state the goal up here on my next thing right here so I don't forget it. So my goal is to prove that the action of mapping class group mod G of L, so that action right there by conjugation is, induces the trivial action on, say, the cohomology, kth cohomology with rational coefficients in some range, right? That's what we want to prove. And so we're going to check this on generators. So there's a basic fact about the mapping class group. So we know we have a very nice set of generators for it. So the mapping class group G is generated by what are called Dane twists. So T sub gamma. So gamma is a non-separating simple closed curve on sigma G, so it looks like, maybe something, you need a whole bunch of Dane twists. Of course, you don't just need one, but, you could just take, that curve right there. Turns out if you just take these ones right there, these ones generated, okay? And now what is a Dane twist? The Dane twist is the following. So there's a sort of picture if you have not seen it before. So you zoom in on your curve gamma. And so let's say we look at a sort of transversal curve. What the Dane twist does is the twist about gamma, so you cut along gamma, give it a full 360-degree twist and reglue. So it looks like this. So then the blue curve, say, goes like that. Okay, so these are the generators to the mapping class group. In fact, yes, you need the ones I listed right there. So it's enough to check that such T gamma act trivially, right? And so now comes the sort of one idea here, which says the following. So let's draw this curve right there. So I'm going to let's say you look at, I don't know. Let's say that this right here, I'm going to draw it maybe in. Yeah, I'll just keep drawing it in white. So let's say that that's the curve that you want to show acts trivially on homology. What you can then do is, well, I want to look that over here. Let's just cut the surface. So over here is a surface that's of genus G minus 1 with one boundary component on that subsurface. The whole thing is sigma G. This one right here just corresponds to the fact that I have a boundary component on that subsurface, namely that right there. Okay, and so I have a map from the mapping class group mod G minus 1, 1 into the mapping class group of the whole genus G surface. This just comes, you have a diffeomorphism on the subsurface, you extend it by the identity to the whole surface. Okay, and so this induces a map from HK. Well, I could do, I could put G minus 1, 1 there. I'll put, say, Q coefficients there. I get a map like this. Let me see. So let me, I like a foolish person, I did not give myself enough room to write that, but thankfully, unlike on a chalkboard, I can do this, right? So I moved that G, I don't even know where that G was. Oh, I know what I did wrong. Okay. Like I had a phantom G there that I didn't expect, and I saw it was right there. So what I'm going to do is I'm going to give myself, well, I get a map from here with Q coefficients. Now, this map is the one that induces homological stability, it turns out. So this map right here, once the genus is large, is the isomorphism homology. But let's add a level structure like this. Okay. And so we'll call this, sigma. So it's enough to prove. So I want to make the observation. So the Dane twist about gamma, commutes with mod G minus 1, 1 of L, right? That subgroup, this is the subgroup consisting of things that are supported on this subsurface over here, right? This Dane twist doesn't touch those at all. It commute if you have a mapping class that's supported over here, it doesn't interact at all with the Dane twist. They commute. And so therefore, it acts, so the Dane twist acts trivially on the image of sigma, right? So this implies that T sub gamma acts trivially on the image of sigma. And it turns out that that's what you end up having to prove. So let me state this on the next slide. So we're going to prove what the key result you have to prove in is that sigma is surjective. So this is, you can see it's right there. So it's enough to prove that sigma is surjective. By the way, so if we already knew that these things were the same as the homology of the whole mapping class group, we'd also know that, in fact, sigma would be an isomorphism. So this is somehow, there's no loss of information in trying to prove that this sigma is surjective. So this is the theorem. So for, let's see, so for G greater than or equal to 2K squared plus 7K plus 2, the map from HK of mod G minus 1, 1L with Q coefficients to HK of mod G of L with Q coefficients is surjective. Once you know that map is surjective, then you automatically get that the Dane twist acts trivially on its image, and so therefore it acts trivially on this whole group right here, and then you get that group, this has the same as the homology of the mapping class group. So that's what you want to prove there. Okay, so this is very similar to, this is a very similar statement. This is very similar to ordinary, so homological stability. And if someone like Craig has spoken to you about ordinary homological stability, you'll know that there is, one second, I forgot to tell my graduate student that I'm giving a talk. So I'm actually giving a talk. Why don't you sit in the last 5 minutes of it? So hi, it's one of my graduate students. Sorry about that. I forgot to tell her that I was giving a talk today. So anyway, so this is very similar to ordinary homological stability. And so you might think, so the first idea you might have is let's try to imitate the ordinary homological stability proof. So you might try to imitate the ordinary H star stability proof. And that is sort of what I do, but there's a fundamental problem. Is that if that worked, it would give you a statement that was true not in rational homology, but in integral homology. This would give such a result in integral homology. And this is false. So fundamentally, this theorem is a rational theorem, and this statement right there that this map is surjective, if I replace the Q with a Z, would not be a true statement. Even for H1, it would fail. So for even for H1, this would be false, and so therefore the machine has to break. There's not a, you know, you can't just run it and hope that things will work out. And so there's a sort of elaborate induction you have to do using it turns out that, you know, you sort of analyze how the machine breaks, and that's encoded in these sort of very complicated local coefficient systems coming from the action of the mapping class group and the homology of covers of the surface. And so you have to run the same sort of argument with twisted coefficients, but then you need tensor squareds of those things and then tensor cubes. And so you end up having to have this sort of induction on like tensor powers of the action of homology on finite covers of the surface. And so those are fairly complicated representations. And so it becomes a sort of elaborate game of chicken between you and that sort of inductive hypothesis. So, thankfully, it just barely works out. Anyway, so that's, I think, all I want to say about the proof of that. And so I think I'll stop there. Thank you.
Any questions, Brandy?
Yeah, could I ask something?
Sure.
Thank you very much for that talk. So with ordinary homological stability, the sort of setup you have is like FI modules or something, where you have a category FI, and you have this sequence of groups, and you regard the sequence of groups then as a functor from whatever category it is to modules over some ring, and you want to try and show that functor is finitely generated, which then gives you a homological stability result. I don't know if that's what you had in mind, but if it is, first of all, is there a category analogous to FI? Maybe it is FI, on which this sequence of groups could be regarded as a functor. And my second question with that is, you comment that you would get a result over Z, but if you took a functor to vector spaces over Q, for instance, you would not get a result over Z, you would get a result over Q. So there's two questions there. Have you got a category in mind on which these things form a functor?
Yeah, so there is a category. So it turns out that this is not the the category that would make the most sense in this context is what you might call SI of Z mod L. So SI would stand for, you have a vector, you have a free Z mod L module, so like a vector space over Z mod L, if that were a field, equipped with a symplectic form. And so an I stands for an injection that preserves the symplectic form, right? And so these do form a module over that category. I'm sorry, Matt. The classes are changing, so I have a horde of undergraduates pouring by my office right now. So it turns out, so Stephen Sam and I, some years ago, I think in 2017 or so, proved that these actually do form a finitely generated SI of Z mod L module. And that gives an integral statement, but it doesn't give the integral statement you want. So you see what that's going to give you, what that gives you is a sort of representation stability type statement. It says that, you know, and that works over Z, by the way. So what it says is that as representations of the finite symplectic group, these things stabilize, but as representations. What I want to show is something much stronger, though. I want to show that they're not just stabilized as representations, but they stabilize to the trivial representation. And so that right there is somehow a sort of less formal and stronger statement. So they do form a finitely generated modular over these categories, but that somehow doesn't give you the statement that you want.
Yeah, well, I'm not completely understanding why it doesn't give the statement you want, but I'll have to think about that. Yeah, the other thing that I was wondering about is very rudimentary. So you know, there must be something wrong with what I'm thinking. But with these subgroups of finite index in the mapping class group, as I think they are, how far do you get with arguments which involve simply the restriction map and the co-restriction map in cohomology? Like, you know, you have, if you do restriction and then co-restriction, you get multiplication by the index, which would be impossible. So one term injects in the other. And if you go the other way and you do the co-restriction followed by restriction, you get a Mackey formula. And with sort of double cosets. And some of those double cosets may then contribute in a way you don't want. Like, does this get you anywhere? Is there a group theoretic approach where you examine these double cosets?
I don't think so. So I think the problem is that, yeah, you get these, well, so these are normal subgroups, right? So double cosets are not a big deal for normal subgroups, but there's just not a formal way to see that you're not getting a contribution from these things. So I think, again, like what you really want to show is not just that these things, you really want to show that all the different cosets give you the same piece, right? You really want to show that the action is trivial. And that's fundamentally different. By the way, so I can answer your, I want to say one other thing. You said, I don't see why knowing that these things are a finitely generated module over this category don't give you what you want. So let me tell you a finitely generated module over that category. You could take something like if you think about, like the skeleton of the category are things of the form, just numbers in, right? You're looking at, Z mod 2 in, it could be standard symplectic form. You could take literally the functor that takes n to, well, Z mod L to the 2n, right? That's a very finitely generated module over that category. But you see this left-hand side here, and the right, like this thing, as you go from n to n plus 1, the right-hand side gets much larger, right? And you see what I want to prove is that in fact it's the trivial representation. So therefore, when you go from n to n plus 1, it doesn't get larger at all. It literally stays the same. So it just is the trivial representation. And that's the fundamental obstacle you have to overcome either in a group theoretic approach or a sort of more sort of representation of categories approach. Is you have to do something that's somehow not formal to show that.
Thanks.
Yeah.
Any comments? Go ahead, Sasha.
Oh, go ahead, Craig.
So with your last statement about this being sort of a homological stability result for these congruent subgroups with coefficients and tensor powers, is this something that can be pulled back from the fact that these are, for each tensor power, kind of a polynomial functor on the mapping class groups, and then sort of restricted to this subsequence, or is it?
I mean that fact does play an important role in the proof, but it's not enough. So, but that's what you need. It turns out that's what you need for the base case of the induction to work, is that statement.
Okay.
So. But these things do form, they do form polynomial functors in an appropriate way. So certainly, I guess Ivanov has, I guess under Ivanov's definition of polynomial functors in the mapping class group, those things, no, actually, I don't, there is a sense in which they are a polynomial functor, and that definitely plays a role in the proof. So I'd have to think about whether it's exactly the same as Ivanov's sense or not, because what you're looking at is not the homology of the surface, but the homology of a finite cover of the surface. And that cover is growing as this, because the deck group is Z mod L 2G, right? So these things kind of explode as you increase.
I wanted to ask you a couple of things. First of all, you told us what doesn't work in the proof of this theorem about surjectivity, but what's roughly the idea that does work? Can you tell us?
Yeah, I mean, so I told you the things that don't work, but what does work is that you take those ideas and you pound them hard and hard and hard and hard, and eventually you just barely make them work. So it's not that the machine doesn't work without having to sort of tweak it at every stage, but eventually, like that is what works in the end. So.
Okay. And where is this polynomial coming from? Is there a reason for this quadratic polynomial? Is that a well-known polynomial? I don't know. It's not the Bernoulli second polynomial.
No, it's a strange polynomial. I don't really have a good. So it comes from. So I told you that I have this sort of elaborate inductive thing, and I have sort of several inductive conditions happening at once, and it causes this thing to grow like a quadratic function. But I don't have any good explanation for it. I mean, it's sort of surprising. And I think in all other sort of stability results I know about, you get linear ranges for when they occur. So I would be surprised if this was actually quadratic, if that was sharp.
Is that quadratic polynomial really coming from basically, as you said, but can I interpret it this way, that it's coming as a product of two linear polynomials?
It doesn't, so actually, I believe it's an irreducible polynomial, but it's something like that. So
Yeah, up to a constant. Like,
yeah, up to a constant. That's more or less what's going on. Yeah.
I see. Okay, got it. Thank you.
Any other questions for Andy? All right, if not, let's thank Andy again for a great talk.
Stop sharing. Stop right there, and now I can see you all. So.
That was actually really fun. Okay, I know we're done with questions, but I want to ask well, I guess the post one. You mentioned like there were k equals 0 and k equals 1, right? Or like results for your main theorem.
Right.
Are they like linear ranges?
Yeah, well, so linear doesn't really make sense in that case. So remember that the range depends upon k, right? And so for k is equal to 1, it turns out that so for H1 it's true for G at least 3, and for H2 it's true for G at least 5. So
okay. So that's
those
probably
are
like
actually not the range. Those are not the ranges given by my theorem here. My theorem gives worse ranges in the known cases because it just does.
Yeah, just something really small. Okay, cool. Yeah, I suppose you have to meet your student about right now.
Yeah, but
so
you're learning about math by listening to this, right? So.
Okay, thanks again for coming in.
Yeah.
Thank you very much for having me. This is, it's somehow it's sort of fun to travel by Zoom, but I'm hoping that, this is one of my last Zoom talks. That's what I'm hoping for. Like the world is becoming like a normal world again.
So I guess we're noted that we are, we're going to try not to get you in for another Zoom. Maybe next time you speak, when we will get you in personally.
Yeah. I mean, so I think I gave a talk. I've now given 2 Zoom talks at Minnesota. I gave a colloquium last year and I gave this talk this year. So I gave an in-person talk maybe in 2018. And I had a really great time visiting. So next time, hopefully I'll see you all in person.
Let me tell you, you don't want to be here today.
Yeah.
I mean, we have a winter storm this week. So,
Yeah, I like it.
I mean, you have winter storms, but look, I live in South Bend. I can't say the weather is nice here, right? So it's not Minneapolis bad, but it's not nice here, So
yeah, that's fair.
But it's also not bad enough. So like the thing about Minneapolis is you can do like ice fishing and stuff like that there that you can't, like South Bend is cold and miserable, but not so cold that you can do things you can do in the cold. So
yeah, we definitely have like skiing enthusiasts here, so I'm not going to bash this weather anymore.
Here in Minnesota, it's cold, but definitely not miserable.
Yeah.
Right.
Although the weather has been warm enough recently that ice fishing is a questionable decision right now. There's a lot of open water on some of the lakes and rivers. So
yeah, well, global warming is going to make it so people can't do that kind of stuff anymore, I guess, right?
They'll just have to fish.
Yeah. Well, so this is what I say, like 50 years from now, Houston will be uninhabitable and South Bend will be pleasant, right? So
It will be truly south.
that's right. Truly South Bend. That's right. Yeah. The United States population will migrate into Canada.
I didn't realize. Habitable.
Houston's not habitable now. My graduate student says she doesn't know that Houston's habitable now.
I am from Texas. Below Houston, actually.
Yep. Anyway, so I should probably go. I should probably talk to my student, but it's a real pleasure seeing you all. So
Thanks.
Yeah. Thanks for coming in.
yeah, bye, y'all.
Yeah.